we're going to start talking about changing energy and work. And the definition of work from physics is maybe not what you would think of in English. Your definition of work is that the work would be equal to the change in energy. Okay? And that will confuse us sometimes because they'll say 20 joules of work are done accelerating a cart. And then they'll say, what's the kinetic energy of the cart? You go, wait a minute, they give me work, they didn't give me velocity, they give me mass, how do I find the kinetic energy? But work is energy. So if they say 30 joules of work are done to accelerate it, it's going to gain 30 joules of kinetic energy. Okay, so that's one way of finding work. Work is changing energy. The other way of finding work is, in order to change the energy of something, I have to put a force on it. So it's going to be Fx cosine theta. Okay, x is the displacement or distance. Theta is the angle between F and x. Now, normally F and x are going to be in the same direction, which means the angle is 0, cosine of 0 is 1, so I can ignore that part and we'll do work equals Fx. But every once in a while we have a problem where the force is not in the same direction and you have to know that you have to take that angle into account. And there will be an example of that coming up. So, we have an example here. The cart slides down a hill as shown. You get the velocity at the top of the hill is 5. We have the velocity at the bottom of the hill is 15. You're given the problem. And we want to find the work done and the force of friction. Now, there are two ways to find work. One is change in energy. One is this Fx equation. Now, when I look at this problem, I look at it and I go, oh, sliding down a hill, that looks like potential energy, kinetic energy stuff. So I'm going to try that rather than trying the Fx cosine theta. So, top of the hill. I can find the kinetic energy. Kinetic energy is 1/2 e squared. So 1/2 times 20 times 5 squared. And that's going to give me a kinetic energy of 250 potential energy. It is H. So it's going to be 20 times 10 times 20. And that gives me 4,000 joules. And then I can find the total. So I would just add those together, and we get 4,250 joules of total energy at the top. Now, if there was no friction in this, we would know that our total energy was going to be conserved. The total energy at the bottom would be 4,250, but that's not going to be the case if we have friction. So we'll find the energy at the bottom. Potential energy is 0. At the bottom, the kinetic energy, we're going to use this equation to find. So, mass is 20, and velocity at the bottom is 15. And that's going to give me 250 joules of kinetic energy. And then the total, since there's no potential, the total is just equal to kinetic. Okay. Now, our definition of work is change in energy. So our work is change in energy. So it's going to be 4,250 minus 2,250 is equal to 2,000 joules is the work done. So the units for work with joules, if work is change in energy, it has to have energy units. And you may have noticed, usually when I do a change, I do final minus initial, and I didn't in this case. I generally don't with work and energy because there's no directions involved. So I generally don't think of final minus initial. I don't worry about sign. Now, the second part of this is to find the force. Well, force of friction. The friction is the force that's causing the energy to change. Okay, so that's the force doing the work. So now I can use this equation for your force Fx cosine theta. Now I want to think about that cosine theta. Okay, x is this way, the way it's moving. The force of friction is that way. They're actually 180 degrees apart, cosine of 180 is -1. Again, I don't really worry too much about sine, so the cosine of theta is 1. So I don't have to worry about it in this case. So now I can just do my work is 2,000 is f. And x is the distance it went. I don't want to use this height of 40. I want to use the distance it went down the hill. So I'm going to use 40 here. I'll use the height of 20. And then I find that the force of friction is equal to 50 newtons. Now, for our next example, we do have that angle going on there. Okay, so we have a 2 kilogram mass being accelerated by 4 newtons, or distance 3 meters, and we want to know the work. So part 1, right, we're trying to find the work. Now, there's 2 ways we could go about work: change in energy or fx cosine theta. This time, it's obviously going to be fx cosine theta. So plug into that equation. So it's 40 times x, distance traveled is 3, and theta is the angle between them, 30. When I do that, I get 103.9 joules. I'm going to do a little aside here. Another way of looking at it, sometimes you'll see it written this way: work equals fx cosine theta. It can also be written. So if I take another way of looking at it, they'll say that work equals the force parallel times x. And what does that mean? Well, this force of 40 newtons here has an x component and a y component. The x component is the one doing the work that's making it move the 3 meters. The y component actually isn't doing anything in terms of work or in terms of changing the energy. So we're only going to worry about the fx. The f of x is 40 cos 30. And then I could do that force times 3 meters. And it's mathematically identical. So you can look at it either way. Now, step 2, what is the kinetic energy gain? You say, okay, I don't have velocities, how am I going to find kinetic energy? The trick is to know that work, okay, is a change in energy. It can turn into kinetic energy if I'm accelerating it, okay? It can turn into potential energy if I'm lifting it. It can turn into spring energy if I'm using the work to pull apart a spring. So work is change in energy. In this case, I'm not lifting it, okay? I'm not pulling the spring out. What I'm doing is accelerating it, so I'm getting kinetic energy. So the change in kinetic energy is going to be 103.9 joules, which is going to be the same as the work. Then I can find the velocity. Now that I know the kinetic energy, okay, so 103.9 equals 1/2. Mass this is 2 times v squared, and that will give me a velocity of 10.2 meters per second. We got another example. Okay, now, in the last unit we said that a graph of force versus time, the area underneath it is equal to the impulse of the force times time is the impulse. In this case, force times distance is work, so the area is equal to the work. All right, so now it says what is the work on the cart? So I'm going to do work equals the area. Okay, that's going to be base times height divided by 2. This is a triangle. It's going to be 20 newtons. That's the height actually times 4 meters divided by 2. That's going to be 40. Now, if you look at these units, it's Newton meters. And that's actually an acceptable unit for work. And it's actually exactly equivalent to a joule. So I can write 40 Newton meters, or I can write 40 joules. And then what will be the velocity of the cart? The cart starts from rest. The work done is 40, so it had 0 kinetic energy. I'm going to work on it, giving it 40 joules of energy. That's going to be kinetic energy. So 2, we're going to say the work becomes kinetic energy, which is 40 joules. And then I can find the velocity, KE is 1/2 mv squared, so 40 equals 1/2, mass was 2, mv squared, and then V is going to be 6.32 meters per second. Okay, to finish off, we're going to do a problem where we're lifting a block, and this is one where it says how much work is done to overcome friction. And these are a little bit tricky, okay? I'm going to make a note that the total energy that we used is 500 joules. It turns out that not all of that was done in lifting the block, because some of it was had to overcome friction. So I have to figure out how much work is done lifting. So I have a 60 Newton block. What does that tell me? It's telling me the force of gravity. So I know that the force of gravity on this is 60 newtons, which means the mass of this is going to be 6 kilograms. And I'm going to lift it a distance of 8 meters. Okay? And we're thinking about energy. So let's find the potential energy that it gains as I'm lifting it. PE gain is going to be mgh. Now the mass of this was 6, G is 10, and H is 8 meters. And that's going to give me a potential energy of 480 joules. Okay? Now, the total energy I put into it was 500, only 480 went into lifting it, so how much was done against friction? So we're going to find the work done against friction. It's going to be 500 total put into it, minus 480 that was for lifting it. That's going to give me 20 joules to overcome friction. So we've kind of lost some of the energy. We put 500 into it, only got 480 of useful work out of it. We kind of lost that 20 of friction, got turned into heat.